high-speed air travel. Before that, let me introduce the moderator. We have Dr. Bala Bharadwat, who is going to be the moderator for this panel, and he's in Bangalore. So he's going to be moderating it from Bangalore, India. Thank you, Bala. I know it's late night for you. We have Mary D'Souza from NASA. We have Dr. Kevin Bocat from Boeing. And then we have Mr. Vic Kachoria as one of the panelists. So let me introduce the moderator. So Dr. Bala Bharadwat is a globally recognized aerospace professional with more than 4 decades of experience. He holds solid academic credentials in aerospace engineering, BTech degree from Indian Institute of Technology, Madras in India, master's and PhD degrees from Georgia Institute of Technology. He also has an MBA from University of California, Irvine. Dr. Bharadwat has worked both in the US and in India. He has held several leadership positions at Boeing and retired as the managing director of Boeing's Engineering and Technology Center in India, the largest such Boeing center outside the US. Dr. Bharadwat has also worked in academia as a faculty member of aerospace and mechanical engineering at Boston University for several years and an adjunct professor at other US universities. During his distinguished career, Dr. Bharadwat has been recognized with many prestigious awards from NASA, Boeing, and other organizations. He is an associate fellow of AIAA. He is also an invited member of the Research Council of the National Aerospace Laboratories in India. Please welcome Bala. Please take it, Bala.
Right. Thank you very much, Shrikant, for that nice introduction. We do have Kevin, who has to bow out a little bit early, so we will start our discussions with Kevin. But before we go there, I wanted to say good morning to everyone dialing in from the US and Canada, and greetings to all our attendees, because we just heard that we have attendees from all across the globe. Welcome to this session on high-speed air travel. It's my distinct honor and privilege to moderate this panel discussion. We have 3 outstanding panelists, and I'll introduce them shortly. But before we get to that, just a little bit of background about why we have interest in this topic. As we speak, we are sitting in various locations across the globe. We are able to connect virtually because of the miracle of modern day electronics. However, there are many occasions when we would really like to meet face-to-face and have in-person discussions. We all want to go places, but don't want to spend too much time traveling from place to place. And we are always looking for a faster way to get there. Now, if you go back in history, in aviation history, in the 1930s, commercial airlines used to travel at about 200 miles per hour. And this was much faster than the cars and trains of those days. So it was certainly an improvement. In the early 1950s, when the first jet transport came along, they flew at around 500 miles per hour. And even today, the subsonic airplanes barely reach 600 miles per hour. In the 1960s, late 1960s, 2 supersonic transports came into the picture, the Tu-144 from USSR and the Anglo-French Concorde. These were technological marvels, flying at about 1,400 miles per hour. But they also had unique challenges, and because of that, they could not compete in the aviation marketplace. Both of these airplanes, were retired well before, the original designers thought they would. In the 1990s, NASA and the US industry came together to explore the technical challenges of building a modern supersonic transport. A lot of good work was done, but eventually it didn't translate into a real airplane. Since then, there have been many pockets of excellence, I would say, looking at the possibility of high-speed flight, and a lot of progress has been made in the last 20 or so years, not only in supersonics, but also in hypersonics, which we will hear from one of our panelists. Today's panelists will discuss some of these challenges and share their insights on high-speed air travel. Now, like I said before, we are very fortunate to have outstanding panelists in this session. Between them, they have more than 100 years of collective experience on various aspects of aerospace, complex systems, and entrepreneurship. They have followed their own unique path, but what they share is a common interest and passion for aerospace. Let me start by introducing Ms. Mary DeJoseph, who is the quintessential NASA technologist and technical leader who has worked on an amazing collection of NASA missions. She has spent most of her 35-year career in aerospace with NASA in various systems engineering, project and program management, and senior leadership positions, both at NASA Langley Research Center and Goddard Space Flight Center. Ms. DeJoseph is currently the Director for Aeronautics Research since 2019 at NASA Langley. She previously served as the Deputy for Flight Projects in the Aeronautics Research Directorate and was also the Director of Flight Projects before that. These are the places where NASA researches solutions to problems from global climate change, access to space, air travel, and future vehicles for aviation. She has contributed to the development of many space-based remote sensing systems supporting NASA science research, including the Aqua and Terra Earth observation satellites, the Tropical Rainfall Measurement Mission, and the Fermi Gamma Ray Space Telescope that was launched recently. As program manager for Living with a Star and later deputy program manager for Earth Science Decadal Survey missions at NASA Goddard, she led NASA's formulation, implementation, and launch of many heliophysics and Earth science missions, including the Solar Dynamics Observatory, Van Allen probes, and the magnetospheric multi-scale mission. You can really say that she is a space scientist. Ms. DeJoseph received a bachelor's degree in mechanical engineering from MIT. Even though she's been working on a variety of space missions, she's a down-to-earth person. She currently lives in Suffolk, Virginia, on a small farm with her husband. She's an avid equestrian, active in the local farming and equestrian community. Please join me in welcoming Ms. Mary DeJoseph to this panel. Next, I would like to introduce Mr. Vic Kachoria, an entrepreneur, a man with many interests and many successes during his career. Mr. Kachoria is the founder, president, and CEO of Spike Aerospace and is leading the development of world's first quiet supersonic jet airplane, the Spike S512. This luxurious state-of-the-art aircraft cuts travel times in half so passengers can enjoy more time at their destinations. Mr. Kachoria has a BA in physics and mathematics from Boston University and an MBA from the MIT Sloan School of Management. He has had a diverse and successful career in technology and finance. Early in his career, he conducted antiparticle research, wrote software for quasar simulations, built a scale maglev train, designed mass drivers for asteroid mining. He then worked at NASA Marshall Space Flight Center in Huntsville and at GE Aircraft Engines at Lynn, Massachusetts. Later, Mr. Kachoria started a company building solar panels and then started, built, and successfully sold 2 technology ventures related to computer-aided design and communications. He went on to spend 10 years in boutique investment banking, mergers and acquisitions, and corporate development. He has consulted on several new ventures in space elevators, air taxi services, suborbital rockets, and solar power satellites. In total, Mr. Kachoria has 35 years of entrepreneurial and executive experience in aerospace and investment banking. In addition to leading Spike Aerospace, Mr. Kachoria serves as an advisor and investor in several early-stage technology companies. He has also received his pilot's license at the age of 17 and is working towards his commercial rating. As you see, he is a man with a variety of interests in desalination, wave, solar, and hydrogen-based energy generation, aerospace, aviation, and space exploration, photography, art, travel, and pop rock music. Please join me in welcoming Mr. Vic Kachoria to the panel as well. The third member of this panel is a colleague and friend I have known for many years. We have also worked for the same boss for some time. But let me tell you, he is definitely the smarter one between the two of us. Dr. Kevin Bocat is an internationally recognized expert with 39 years of experience in hypersonic aerodynamics, propulsion integration, and vehicle design and optimization. He holds a BS, MS, and PhD degrees in aerospace engineering from the University of Maryland. Dr. Burkett is a principal senior technical fellow and chief scientist of hypersonics for Boeing. He's also a fellow of the American Institute of Aeronautics and Astronautics, a fellow of the Royal Aeronautical Society, and a member of the National Academy of Engineering. In 2021, just recently, he was selected by Texas A&M to be a fellow of the Hagler Institute of Advanced Studies. During his distinguished career, Dr. Bocat has had several notable accomplishments related to hypersonic vehicles, such as developing the viscous optimized hypersonic wave rider, flight testing scramjets by launching them from a light gas gun, technically supporting the NASA X-43A scramjet flight test program, originating and optimizing the design for the X-51A scramjet-powered demo vehicle, helping the Space Shuttle Columbia accident investigation by performing some complex simulations, leading Boeing's contributions to the HIFIRE International Hypersonic Flight Experiment Program, and leading Boeing's hypersonic passenger airplane design investigation. During the spring semester of 2007, Dr. Bocat was a visiting professor at Princeton University, where he taught a course in hypersonic airplane design. Dr. Bocat leads Boeing's advanced design and technology development efforts for hypersonic missiles, airplanes, and space planes. Please join me in welcoming Dr. Kevin Bocat to the panel. We'll start with brief presentations from the panelists. First, I would like to invite Dr. Kevin Bocat. He has another appointment to go to. So, we will listen to his story on hypersonic vehicles. Kevin, over to you.
Thank you, Bala. Thanks for the kind introduction. Can you hear me okay?
Yes, yes.
Very good. All right. So if you would go to my first slide. I've been doing hypersonics my entire career, dating back to my PhD work at the University of Maryland, where I met AJ Kathari and Mike Griffin. I've known them both for about 40 years. So it's fun to be here with them, together with them this morning, and speak to you a little bit about really about the culmination of my career. Everything that I've done from graduate school till now kind of led up to what I'm going to talk to you about today. So if you go to the next slide, please. Several years ago, Boeing started a project. It was a corporate-wide project looking at the future of commercial transportation in the areas of urban travel, regional travel, and international travel. In the area of international travel, we looked at supersonic and hypersonic transportation, and I had the privilege of looking at investigating the hypersonic problem. So here we asked the question: could you take an international trip that's typically, by necessity is several days long, because it takes, a half a day to fly across the ocean or more, and could you turn that into a revolutionary time savings and even make it a one-day trip, flying, say, from from California to Tokyo and back in a day, or flying from the East Coast to Europe and back in a day. So we asked that question, and we investigated what would be the airplane design and the technologies, and how fast would you have to go to do that. So you see that plot on the right. That is a plot of the time savings as a function of speed to get from LA to Tokyo, as a function of cruise speed. And it accounts for, the number one is just a 787, takes about 12 hours to fly across the ocean. And then what fraction of that time does it take to get there as you go faster and faster? And this plot takes into account the reasonable level of acceleration that you can achieve with an air-breathing engine, accelerating up to a speed, then cruising, and then decelerating. And what you'll notice for that range, that you asymptote out at about Mach 5 to 6. You really gain almost no benefit flying faster than Mach 5. So the knee in the curve is about Mach 4. So Mach 4 to 5 is about as fast as you can go. The world's not big enough to really take advantage of going much faster than that, unless you could accelerate at extremely high rates like a rocket would do. That would change it a little bit, but of course that's not going to be as comfortable for a passenger. This airplane, people often ask me, what will it feel like? Well, it'll feel like taking off, but accelerating down the runway for takeoff, but that acceleration will last for several minutes. You'll just feel that same pushback in your seat. And after a few minutes, you'll be flying at Mach 4 or 5, and you'll be at near 100,000 feet, and you won't really feel anything different than that. You'll get a great view of the curvature of the earth and the blackness of space above you. It'd be a pretty neat ride. So we focused in on that Mach 4 to 5 range, and really focused in on 5 to see what was required to fly at Mach 5. So the design, and actually it's only been about a week and a half now that we've shown more what this airplane really looks like. We used to use an icon for the vehicle, and this is more what the airplane really looks like. So some of its features are what we call a wave riding wing. This was work I did in my PhD. It's an optimal way of designing the aerodynamic shape to achieve efficient aerodynamics and high lift to drag ratio. The engine is a very unique, I can't talk a lot about it, but it's a very unique combination of technologies for what we call a turbo ramjet engine. And it's actually based upon an existing commercial engine core. So it's a core that we don't have to invest billions to develop a new core. It's got some other technologies in it, like a ram burner, which is also an afterburner, and some cooling technologies, but it's fundamentally based upon an existing engine, which is kind of a big deal. It's made from the temperature it would achieve at cruise is 11 to 1200 degrees on most of the surface. So there are advanced titaniums that can withstand that kind of temperature. Internal structures might be some composites, say for the cabin. It's got advanced three-dimensional inlets and nozzles. We've got advanced computational tools today that allow us to create much more sophisticated airframe propulsion integration. There's also a lot in the area of thermal management. We have numerous innovations, many inventions have come out of this work. And some of those are in the thermal management area, very unique ways of managing the thermal for environmental control, for the propulsion system itself, and it even generates power in the process of doing that. And then we envision a vehicle like this to actually have synthetic windows. It won't look different for you if you were inside, it'll look like looking out a window, but we have the technology now to do that, and that helps thermally and structurally as well. Now, with current world conditions, we paused this work. We paused looking at it from a commercial airplane perspective, but we continue to look at the airplane design for other applications. So that's an important point. If you go to the next, one more point. It's also over 20 years of looking at how to get to space in a very routine and affordable way, instead of maybe once every month or so in a rocket, where you're throwing away parts of that rocket and having to strap yourself in and pull a lot of G's. What if we could fly into space more like an airplane? And it turns out over 20 years of research, we found that an airplane like this could could carry a second stage that would get to orbit, and it could fly, routinely once or twice a week, and dramatically reduce the cost and increase the routine nature of getting in and out of space. So next slide, please. I'll just touch now briefly on some of the reasons why today, what are some of the things we have today that we didn't have in the past? Why can we do this today where, say, the Concorde at Mach 2 was challenged? Why can we do Mach 5 today, or even make an economically viable system where we struggled with that before? So we've got a lot more technology today, and a key one is computer-based modeling and simulation. And under that, using those methods to do what I call multidisciplinary design optimization. We have the capacity today to design a vehicle where you can create synergies between aerodynamics, propulsion, control, thermal, structure, and create synergies that we could not achieve before with basically, traditional engineering design methods. And that allows us to get much more performance out of a system. Propulsion advances, our engines today are much more efficient, lighter weight, a high temperature, which gives you efficiency. We have advanced endothermic fuels, which means we can use the fuel, the chemical nature of the fuel, to absorb heat by chemically cracking it. And we've developed systems that can fly from Mach 0 through supersonic and even to hypersonic through multi-mode approaches. We've got much more advanced high temperature materials, both metal and ceramic, lighter, stronger, longer life. New manufacturing technologies like additive manufacturing. What that buys you is you can create structural topology shapes that are much more efficient at transferring load. In other words, they're lighter. So between materials and structural design, we can make lighter structures. Advanced thermal management, I've already talked about. We have some really neat thermal management systems being developed both for the energy sector and aerospace that are beneficial in both areas that are enabling. Lightweight, high power electric systems, we move more and more towards electric, and those technologies are making things lighter. And we have a much larger global economy and greater personal wealth today, which, from the economic side, we believe is enabling. Next slide, please. There are still several challenges. Technologically, we can, are you switching to the final slide? Yeah, there we go. If you could switch to the final slide. It's not changing. That up to me, maybe I'm supposed to change it. Okay, so sorry about that. There's still, even though technologically and from a design point of view, we could design this plane today, we have everything we need for a Mach 5 airplane. There's still many challenges. Inlet and nozzle design is a big one. If you look at a hypersonic plane, it's interesting. You've got to have inlets and nozzles that operate all the way from takeoff to Mach 5. And at Mach 5, you need a much bigger inlet than you needed, say, Mach 1. In fact, it needs to be 3 times bigger. So how do you design an inlet that can take on 3 times more air at hypersonic speed than at Mach 1? If it's that big, what will it do at Mach 1? Well, it'll spill a lot of air and create a lot of drag. So a lot of innovation and invention went into designing an inlet can operate efficiently, low drag, high compression efficiency at those extremes of speed, and same in the nozzle area. Stability and control, aerodynamics changes dramatically as a function of speed, and that changes stability and control. And how do you accommodate that? Again, going back to optimization allows us to do that. Hot joints, control actuation, wing surfaces are very thin. How do you build that actuation into a thin, hot environment? Fluid thermal structural interaction. As things get hot, they deflect and bend. So your aerodynamic and your propulsion shapes will change, and you have to accommodate for that. And then getting into the environmental aspects, we all know that CO2 is a greenhouse gas, but water is too. And the altitude at which you emit these at have an effect. We can use sustainable aviation fuels and mitigate CO2, but how long it persists in the atmosphere is an issue. And these are not totally understood at this point and need further study. So it's not just the fact that we can close the cycle and say no net CO2, but how long does it actually stay in the atmosphere as a function of altitude? And of course, we're flying much higher. Ozone depletion is another one. There is NOx emissions and water emissions, and both can affect ozone, and again, that's a function of altitude. Sonic boom limits overland flight, but an interesting factor, the higher you fly, the lower the boom. So it seems counterintuitive, but if you fly faster and have to fly higher, you may actually limit the boom. And then certification and regulation is a very different vehicle. It's hot. You have a system that now has to cool the outside air. If you slow down the air to bring on board the airplane, it's 1800 degrees Fahrenheit. When you go from Mach 5 to Mach 0, that air is 1800 degrees Fahrenheit. Obviously, that can't go into the cabin, so you have to cool that air, and you have to be able to certify. That's got to be a certifiable system. And the hot structures, higher takeoff and landing noise are a necessity due to low bypass engines, and how do you integrate into the national airspace? So there's still challenges before us, despite the fact that we have technologies. We continue to look at this airplane for other applications, and it's very exciting. There's lots of challenges, which is what makes the problem fun. And with that, I thank you for your time, and I'll turn it over to my next panel. Thank you.
All right. Thank you, Kevin, for that great update. Yes, the technologies are there, but then we still have some ways to go, probably. Next, I would like to invite Ms. Mary DeJoseph. NASA, of course, does a lot of technology development work, and I think Mary is going to share some of that relative to high-speed travel. So Mary, over to you.
Thank you, Bala. So I want to remind everybody that the first A in NASA stands for aeronautics. We explore technologies that reduce aircraft noise and fuel use, get you gate to gate safely and on time, and transform aviation into an economic engine at all times. Next slide, please. We're facing global challenges. The aviation industry is global in scope and impact, and the demand for mobility will continue to grow. The aviation system must be sustainable and safe, and aviation continues to transform our economy and society through innovation, leveraging convergent technologies inside and outside the aviation sector. NASA plays a critical role in leading the transformation of global aviation with efforts focused in strategic thrusts. One of those major focus areas is innovation in commercial supersonic aircraft. Next slide, please. So why innovate in commercial supersonic flight? Well, higher speed will transform the air travel experience for long distance flight. We can reduce flight times by a factor of 2. As you'll hear, the high-speed aircraft market is attracting the interests of many US innovators, and there are several new market entrants working in supersonic aircraft with plans to roll them out for first flight. NASA contributes science and technology to expand access and sustainability for these faster than sound vehicles. Next slide, please. So major challenges to high-speed flight. You heard all of these more or less from Dr. Bocat before: sonic boom, high altitude emissions, efficient performance and operations in the airspace, and takeoff and landing noise. So while our long-term goals at NASA are to address the challenges related to fuel efficiency, emissions, and noise during takeoff and landing, our current priority is focused on the sonic boom challenge, and that's what you'll hear about for the rest of this presentation. A major challenge to flying at supersonic speeds over land is a loud sonic boom that is heard by people on the ground when an aircraft is flying faster than the speed of sound. NASA is working on quieting the boom and transforming the future of aviation. Our Quiet Supersonic mission is a comprehensive, scientifically driven effort to provide US and international regulators with statistically valid data required to approve new rules that will allow commercial supersonic flights over land. Next slide, please. NASA is addressing the unique barriers to sustainable, environmentally responsible, high-speed flight to enable global access and connection. The centerpiece of this effort is NASA's X-59 Quiet Supersonic Technology, or QUEST, an experimental aircraft shaped to reduce the loudness of a sonic boom reaching the ground to that of a gentle thump, or if a sound can be heard at all. A thump may be equivalent to a car door slamming across the street. Our near-term focus is on overland flight with this aircraft. The quiet overland flight is the principal barrier to opening a civil supersonic market. And new international standards based on response data from a large diverse population are required. NASA is ramping up efforts to address the broader sustainability challenges. We are initiating a new effort to address airport community noise. Our longer-term research portfolio also addresses high-altitude emissions. And these are all synergistic with sustainable flight technology for subsonic aircraft fuels and airspace operations. In investigating the potential of even higher speed flight, we have initiated some studies with industry on the commercial viability of higher than Mach 2 flight. So in executing all of this, we hope to prove out that our NASA shaping technology, that long skinny nose in front of the aircraft, actually does perform as projected and quieting the boom to an acceptable level. So let us gather a convincing data set for the regulators, and will help us create a new environmental standard for overland supersonic flight noise. This is a major effort that represents our commitment to create the needed data for new rules that will enable supersonic flight overland. Next slide, please. We also have extensive plans for community testing after the X-59 aircraft has been delivered for first flight sometime later this year. We are still in the process of selecting the overland test flight sites to gather the data. This project and the mission, including this community response test campaign, is a comprehensive, scientifically driven effort to provide US and international regulators with statistically valid data required to approve those new rules. NASA will provide the results of this community survey and the X-59 acoustic data collected during the community overflight tests to US and international regulators for use in considering new sound-based rules to enable supersonic flight over land. If the rules change because of NASA's data, a new fleet of commercial supersonic aircraft become viable, allowing passengers to hop on a plane and arrive from destination in half the time. And that final slide. And for more information, follow us at any of these social media and news platforms. We look forward to a really exciting flight campaign with the X-59 aircraft in the future. Thank you.
All right. Thank you very much, Mary, for bringing us up to date on what's happening in NASA. We may have some follow-up questions after we hear Vic. Vic has got a supersonic airplane that he's building. And Vic, over to you. Let's hear about the supersonic airplane, which sounds a lot slower than the hypersonic, but remember, it's supersonic and much faster than what we do today. Over to you, Vic.
Thank you, Bala. I appreciate the introduction. And I'm not building the supersonic jet by myself. Obviously, I got a large team of executives and engineers working with me. But I have to say, on this call and hearing all the panelists that are here, the introductions from Shrikant and Michael Griffin and others, that I'm very humbled the amazing amount of engineering talent and experience on this call. It's inspiring. I don't have a PhD. I only have a basic physics degree, and I used it briefly for a few years and moved to the dark side, to the business side. Most of my career has been building companies and in technology, using my physics to build companies. But as Michael Griffin said earlier, our math skills fade as we get older. Mine faded probably immediately after I graduated. So I depend on my engineers and the others to do the math and the hard work. I just ask some silly questions and always throw wrenches in the work. So I welcome everybody, all the attendees to this call. I wish you all a very prosperous and happy and healthy 2022. This is a tremendously exciting time for me, and I think for the world, to be in aerospace and aerospace engineering. Technology is growing. It's not just growing at a steady pace, as we've seen in computer technology or TVs or cars. It's growing at an accelerated pace. The developments that we've seen in cars alone in the last 10 years is more than we saw in the last 100 years. And I expect we're going to do the same thing in aerospace, that the developments that are happening in this decade, in the 2020s, maybe beyond and continuing beyond that, is going to be phenomenal in every aspect of aerospace, air taxis, going to the moon, going to Mars. So many innovative companies starting up, established companies, NASA and Boeing, the Indian Research Organization, the Japanese, the Koreans, the Russians. Everybody is so passionate and excited. What's happening is you're taking all the technology that's been developed over the last 50 or 60 years in computers. Computers are an enabling technology to aerospace because of this availability of computers and high-speed computers. We don't need a Cray computer anymore. We can buy a $10,000 desktop computer and do the work that a Cray computer used to be able to do. Anybody can do it, an engineer at the desk. It's phenomenal what we can do these days. Material science has advanced, electronics has advanced. The things that we can do today is tremendously exciting, and I'm looking forward to that future. Thank you. Next slide. Thank you. We've already talked about the speed of supersonic and what it offers, as Bala mentioned, cutting flight times in half. Kevin's remark, cutting flight times by 4 or 5 times. That's tremendously exciting. I'd rather do that. Never mind supersonic. If we could fly hypersonic, I'd be doing that tomorrow. I travel quite a bit for work, conferences all over the place, and sitting on a plane for 12 hours is quite exhausting. If I can do it in 2 or 3 hours, I'd be doing a lot more traveling. And for me, travel is building relationships, being able to go to Europe or Middle East or India. I get to connect with people face to face. Zoom is fantastic, and it's enabled a lot of work to be done, and enables this conference. But by shaking hands, looking somebody in the eye, having dinner with them, that's phenomenal. That's how you build relationships, and I enjoy it, and I miss it in the last year and a half, 2 years. So supersonic exciting. This is New York, and this is a typical range map that we probably are all familiar with. Cuts flight times from New York to London by half. So if we can go to the next slide, you can do a similar flight maps, range maps from Delhi to the world, from New Delhi to anywhere in Europe, Asia, New Zealand, Australia, and Africa. Is a day trip. You can fly to London in 4 hours and fly back that afternoon, even at supersonic speeds. You don't really need hypersonic. This is cruise time. This isn't total block time. So it's exciting. And I look forward to it. I think there's a lot of people that would love to be able to fly to Delhi to London or Delhi to Beijing. Maybe someday you could do a commuting trip from Delhi to Bangor. I don't know. That seems a little extravagant, but it's possible, I suppose. Let's go to the next slide, please. So as we saw on that map, most of those flight routes are over land. As Mary suggested, the sonic boom is absolutely critical. You can't fly over these populated regions, create a sonic boom, disturb people on the ground. It's not just people. You got migratory animals, you got birds that are going to be disturbed by the sonic boom to pass by them all the time. You got sensitive structures that are going to be weakened by the sonic boom flying over them constantly. So sonic boom is a huge issue, and it's one of the reasons that killed the Concorde or prevented expanded use of the Concorde. Maybe it would have been more successful if that hadn't been an issue. So this is absolutely critical, mitigating this. And next slide, please. Don't know what I have next after this. If we can go to the next slide. The other issues, as Mary talked about, is also the emissions. Absolutely, emissions are absolutely critical. It's a growing concern. The drumbeat's getting louder. Everybody in the industry is very cautious of it, understand that fuel burn is critical, greenhouse gases, as Kevin talked about, carbon dioxide, even the water emissions if you have hydrogen aircraft flying at those altitudes. These are all considerations that have to be mitigated, have to be addressed before you can launch a new fleet of supersonic or hypersonic aircraft. Community noise. Every time a plane lands at an airfield or takes off, the noise is 80 to, well, around 100 plus dB, depending on where you are, how far you are from the airport community. And FAA Stage 5, Chapter 14 requirements require that all to be mitigated down to a much lower level. And that's a challenge. How do you have much engines? You can have much larger engines, air intakes that reduce the noise, but they don't work on supersonic aircraft that create, as Kevin mentioned, too much drag. So you can't have a large high bypass engine on supersonic aircraft. It's a challenge. How do you mitigate that? We talked about the sonic boom, and that's what Mary's group is working on with the X-59 demonstrator and other technologies that are being developed. These are all the environmental concerns for building a supersonic or hypersonic or any other vehicle that we're going to create in the future. These are challenges. So next slide. Yep. So taking all of this into consideration is the company has developed the Spike S512 supersonic jet. This is our artist rendering of it. The aircraft does not look exactly like this. There are a number of differences from this and the actual aircraft we're developing. As Kevin talked about in his aircraft, it's windowless cabin. There is no windows. That black line there is not a transparent window or transparent aluminum. It's just a black line. It could be a tree, it could be a landscape or anything else. Inside of it is a digital screen. We have flat screens that are much lighter than windows. You don't need all the engineering constructs to build a frame for the window. The fuselage is stronger. You reduce the noise coming into the cabin by 20 dB. That's tremendously exciting if you can do that. That's just one of the smaller innovations. But in addition to that, we have to consider the engine inlets, the noise, the sonic boom, fuel efficiency, structural, and all the other considerations that go into any aircraft, but particularly supersonic. Next slide. As Mary suggested, there are lots of companies developing and researching supersonic flight and hypersonic. Our company, Spike Aerospace, is, I think, a really compelling vision and a product to meet that interest, that what we see as market demand, significant opportunity. Boom is another company that gets a tremendous amount of visibility, and they're doing tremendous work. They recently got a Air Force grant to work on a high-speed transport, I think, for the president. I'm not sure if that was the focus. Ariane unfortunately folded back last April, and that was sad. I knew a lot of folks over at Ariane, the executives, a fantastic team that had been working on it for 20 years, 20 plus years. Really great group. Unfortunately, market economics, global economics, Boeing struggles at that particular time, and probably many other challenges we're not aware of caused their demise. And fortunately, most of those engineers have moved on to amazing new careers. In addition to these four, the slide doesn't have enough space for Miss Virgin Galactic, but NASA and JAXA, ISRO, Japanese, Koreans, and everybody else, all the other national organizations are also working on supersonic. Hermes is working on a hypersonic vehicle, great guys over there. Exosonic is also got some grants from the Air Force. Gulfstream has been working on it for 40 years, and Boeing has its own entity. And there are probably another dozen companies I'm not even aware of. Next slide. So one thing I do with all of my engineers, I come from, as I said, a technical background, but I've spent most of my career in business. And I unfortunately always ask, where's the money? Show me the money. How much is it going to cost? How much am I going to make? How much am I going to make is the bottom line. If I don't make money, I can't do it. I haven't ever counted on government grants. I don't like doing things that way. I want any venture I undertake to have a business proposition and a value proposition to the customer. And it makes money, it's sustainable on its own. and not subject to the whims of political needs. So I take my engineers, they're all fantastic and they're experts in their fields, and we spend a lot of time talking about business. And I wish every engineering program had a business course that their engineers were required to take. I find it really frustrating when engineers, including myself in those years, think about how cool the technology is and think about how exciting it is, but forget about that. It costs money, it takes time, and there's a return, there's a bottom line, and that needs to be considered even before you consider the engineering. Somebody like Boeing and NASA, they got lots of money. Sorry, guys, making fun of you. You know, they can do a lot of advanced research. They can undertake this fantastic world, and that's great. But if you're building a product and you want to be an innovator, an entrepreneur, the first thing to think about is the bottom line. There's a lot of bullets here. I'm not going to go through all of these, but how much money does it require? That's a complicated question. It's not just how much money. I mean, it's going to cost us $4 billion. It's with the timing of that money. Where is it coming from? What are those investors looking for? How does it all work? Every one of these bullets needs to be really understood if you're going to build a company, if you're going to build any new venture. And I think a number of the new entrepreneurial companies are looking at these, and some, you know, maybe more focused on the engineering. You know, I wish them all the best, and they all have different approaches. Thank you. Next slide. I was going to say, from in my companies, I've had I think 5 companies over the years. Every one of them has launched a new entrepreneur. I don't know if it was because of me or in spite of me. Fortunately, none of them have gone on to compete with me. That's good. But you know, I'm really proud to think that I've fostered entrepreneurial spirit and helped engineers launch their own companies, or other staff to launch companies, using perhaps some of my ideas, or perhaps they created their own and ignored mine. That's great. So Spike has been around for a while. We've gone from early concept stages to structural design, propulsion. We've done a lot of simulation work, and we have a long ways to go. We're not ready to build the aircraft yet. I've put a lot of money into it. It's funded from the management team and private investors. We're doing well. We're excited about it. We're very quiet about what we do. We don't put out a lot of press releases. We don't talk about it a lot. But I think it's a tremendously exciting future, whether you're looking at supersonic or hypersonic, air taxis, or any of the other fields that are being explored. I'd love to do asteroid mining. That was my high school and college project. The maglev train is a mass driver by Professor Gerald O'Neill from Princeton University, talking about building, mining asteroids and launching material into orbit to process it. I think that'd be tremendously exciting. I just don't find the business value proposition that works today. But someday down the road, that'll be great. There are a bunch of other slides after this, but I think I'm going to leave it here in the interest of time, and allow Bala to take over and ask questions if they need to. Thank you.
All right. Thank you, Vic. These are certainly exciting times, whether it's a supersonic airplane or a hypersonic. I think definitely something to look forward to from the technology side, as well as from the effects they create, you know, for the public. And I think Shrikant was talking earlier about impact on STEM and interest of people who might be interested in, you know, STEM in general or aerospace in particular. You know, you see the people on this panel. You have a variety of backgrounds, and you know what they have been able to do in their lives, you know, in the field of aerospace, as well as outside of aerospace. It's just exciting. So you just have to get yourself educated and get into the system and start doing your thing. Now, Kevin, I know you had to leave. How much time do you have? Because there are a few questions popping up specifically addressed to you.
Yeah, 1 minute.
1 minute.
I apologize. I actually have another speaking engagement of all the strange things on a Saturday.
Right. Well, you know, very popular guy. What can I say? So let's see. We'll take one question from the audience. I think there was a question about how many people this airplane that you showed can hold, and also let's see. The other thing that I would ask you is about what do you see as challenges from the regulations? You know, FAA certification, what do you see? So 2 questions folded in there for you.
Yeah, I'll quickly address them. We actually looked at a range of passengers from as small as 10 and as many as 200. I think 200 is likely beyond what the economics would support. So we kind of focused in on the 10 to 20. 10 is more like a business jet. 20 is more like a first class cabin. And so the sweet spot's probably somewhere in there. Maybe it's as many as, 30 or 40, but that's the range over which we look. So it really looked at it parametrically. Yeah, the certification issues, I touched on that a little bit. You're going to be certifying systems that have never been certified before. Thermal management, how do you? What about decompression? At 100,000 feet, you cannot decompress. So you got to have a certifiable system that prevents decompression. We actually had some pretty clever ideas of how to do that. Because your body can't absorb oxygen at 100,000 feet altitude. That's why SR-71 pilots wore pressure suits in case they had a decompression, they could live. So there's unique challenges like that. There's, we've already talked about noise challenges. The sonic boom, I saw a question on that. It's interesting, again, the higher you go, the less the boom. And as Mary talked about, you can do shaping specifically for boom. We haven't done a lot of that in hypersonics, but we believe that that's also possible. So and even down to, how do you get an airplane that's flying at 100,000 feet and gets reinserted into the normal traffic patterns? That's another area of that would have to be worked out. So with that, I apologize. I'm going to have to switch over, but it was really fun speaking, and I appreciated the opportunity. Thanks all. Bye-bye.
All right. Thank you, Kevin.
Thank you, Kevin, for joining us. I really appreciate it.
Okay. Hey, Shrikant, how much time do we have? Look, my clock says it is 1 hour is up.
Yeah, I would take a few more questions.
Okay.
I know we're running a little bit late, but take a few more questions.
Okay. So maybe this is a question that Mary can shed some light on. There's a question from Mr. Ravi Sharma, says, give us a status of JPDO, ICAO collaboration in managing aerospace for such aircraft. I'm assuming you, I don't fully understand the question. I hope you do.
Well, we have a lead for the low boom flight demonstrator mission, Dr. Peter Cohen, who is coordinating between NASA and ICAO to deliver that high-speed overland flight database to ICAO for Cape 14. And that's our interface to influence the international regulations for overland supersonic flight noise standards.
Okay. Thank you, Mary. I think, Vic, this one I will direct to you. This is a question that comes to my mind. With so much happening around the globe, so much interest in aerospace around the globe, and we all know that these are big challenges, both in terms of technical solutions we need as well as investment solutions we need. So how do you envision a global development of these kind of complex aircraft?
I think any substantial aircraft project is going to be global in nature, particularly for a small company like Spike Aerospace. Boeing potentially could take it all on themselves, but I think they'd be better suited to work with global partners. One thing that does is it enables buy-in from other countries in their regulatory environment. So that's critical to have their buy-in, their support, economic and regulatory. Spike is already working with Tech Mahindra, the Indian engineering organization. We have other relationships in India, in Korea, and all over Europe. So we are already a global enterprise in terms of our relationships. We're also setting up an office in Europe. So it's absolutely going to be a global thing. We're collaboration for servicing and support of the aircraft. The investors are going to come from all over the globe because they're also going to be the customers of a supersonic jet, particularly our size aircraft. So there's tremendous interest from every corner of the globe.
Okay. A similar question for you, Mary. I know historically NASA has been developing technologies, but the US generally tended to be the first user. In some cases, we also have some restrictions in terms of the data becoming available broadly. But again, given the geopolitics of these days, do you see anything being different from NASA side, or will it be continuation of what NASA has been doing over the decades?
So if I understand the question correctly, you're asking about our data transfer and data sharing policy with international partners. And there are mechanisms to partner with other government agencies internationally when we have a joint research interest with mutual benefits. We still have restrictions on transferring technology to international commercial entities, and I am going to defer actually to NASA's legal counsel and Office of International Relations to help me better define that. I am not seeing a big change from the activity I have seen so far.
Okay. I think we're going to be coming up on the conclusion of this session. Just one more question to both of you, referring back to the comment that Srikanth made. I believe there are many youngsters here who are potentially looking at, having careers in STEM. In just a few words, what would be your advice to these youngsters who may be listening right now, or maybe listening to the recordings later? We'll start with you, Vic.
I think there's an awful lot of opportunity to be involved in aerospace and the future of aerospace, whatever aspect you might be interested in, going to Mars and Pluto or beyond, or something closer to home. Obviously the engineering fields, but so many other aspects: legal, regulatory environments, economics, human factors, biology. There's any field that you may pursue is probably something that the aerospace industry will need and want to work with if you show an interest. But I think one thing I see, I get a lot of resumes, and the people that I'm interested in are people that have taken their own initiative beyond the academics. Everybody can take an engineering course or whatever course, but it's the ones that actually go off and build a plane, a small RC plane, or design their own, or design anything, a solar panel. I want to see initiative. If they don't show that, then it's hard for me to know what is their real passion here.
Okay,
thank you.
Great response, Mary. What would you say? What would be your advice to these youngsters?
So everything that Vic said, and get yourself a broad background. There's a place for deep technical experts, but the way technology is converging in the current day and age, having that ability to look across multiple disciplines and integrate those multiple disciplines into new solutions is becoming a really valuable commodity. We really value systems thinkers and the ability to go deep in one area and broad in a whole bunch of other areas.
Excellent. Yeah, I couldn't agree with you more. I think the days when you could be a specialist in one area and contribute a lot, I think those are probably behind us. The excitement is at the interface, the junction of various technical disciplines, and like Vic said, it actually goes well beyond technical. There are many other, what you would normally not think of as engineering, but many other aspects that come in. And any knowledge, exposure, interest in those areas would certainly helps. That's true not only for youngsters, but also for those of us who are still, working and trying to develop our careers. Hey, with that, I know we overshot a little bit here. Thank you both. And Kevin is not here, but I think great presentations from you all. A lot of information shared in terms of where we are, what some of the challenges and opportunities are in this high-speed travel area. And I certainly am going to look forward to how some of these programs are developing, and hopefully one of these days get to fly on a supersonic transport. Maybe it's the one from Spike Aerospace, but certainly looking forward to that. Thank you again. Back to you, Shrikant.